All right, we're going to be starting applications with implicit differentiation, which is our related rates. So there's two things you want to look at. What are we looking for, and what are we taking the derivative with respect to? So that's the bottom. So in this problem, we're going to be taking the derivative with respect to time, dt, and that will allow us to create a dv dt. So when we take the derivative of v, again we get 1, and then that becomes dv dt. Just like the x would be 2x, and it would become dx dt because it's not a t. And the derivative of 2x is 2, but again, it's not a t. So we're going to be taking the derivative with respect to a different variable that's actually in the problem, and that'll give us the rate of change with respect to time in each of these. Now this one asks us to find dv dt, and so it's done. dv dt is equal to 2x dx dt plus 2 dx dt. Now we can also write this as v prime, and so 2x x prime plus 2 x prime. It's your personal preference on which one you want to write, but if you do write the v prime and the x prime, you've got to remember that it's with respect to time in this case. Let's try another. So on this one, we're doing the same ddt, so derivative with respect to time, or t in this case. I guess it could be anything we want it to be, but we're going to be using time. So, all right, so when we do this, it would be 6p, but then it would be dp dt minus 6x, and again, dx dt equals 0. So once you have an equation, we just take the derivative implicitly, and then you look and see what you're looking for. So we're looking for dx dt. So I'm going to rewrite the whole thing, but then I'm going to put my dx dt in red so it stands out. So that is what we're looking for. And again, you can change it to an x prime. That would be fine. So you know me, I like my primes. So that would be p prime minus 6x x prime equals 0. And now we just solve for x prime like we've done before. So negative 6x x prime equals, and then negative 6p p prime, and then we solve for x prime, which is negative 6p p prime over negative 6x, and then we just throw away the negatives because the negative divided by a negative is a positive. Oops, there's actually a 6 in there too, so let's delete our 6 as well, and there we go. X prime is equal to p prime over x. So that is what we're going to be using them for. We're going to take the derivative with respect to a different variable. And then we're also going to have to find units. So if b represents the distance an object falls in meters, and t represents the number of seconds, then what does db dt represent? So again, we always want to write out our letters. So b is our distance, and it's in meters. T is our time, because it's seconds. And then we can write what db dt represents. So it's the same stuff we've been doing, it's just different letters. All right, so now we have our distance over time, and that's going to be in meters per second. So interpreting this, right, the db dt just represents our instantaneous or approximate. I'm going to put instantaneous rate of change in height or distance. We'll put distance to keep it the similar. Distance per time, and those units are meters per second. Oops. So it's our instantaneous rate of change in the distance per time. So it's basically the speed our object is falling. How about this one? So p represents the price in dollars, t is time, x is units. So p is our price, and it's in dollars. T is our time, and it's in, we don't know. It's not given. And so x is our units. And units are units. It's like one object, one thing being made, purchased, sold, one item. All right, so dPTT then would be our price per time, and that's dollars per we don't know. So dPTT would represent, it's our instantaneous, keep doing that, instantaneous rate of change. And you don't have to say instantaneous rate of change. You can just say it's the rate of change in price per dollars. We all know what it means. So it's the price per time. Instantaneous rate of change for the price per unit of time. And again, that would be in dollars per second, hour, day. It's most likely going to be day. It could be years though too. So instantaneous rate of change for the price per unit of time. So we get to see how is the price changing with time by taking the derivative with respect to time. And then we can do the same thing with dx. This is the units per time. So again, it would be the rate of change for the price, or so not the price, the rate of change for the units per unit of time. And it would be units per time. And again, this is at some unit. So if you plug in like, say t is time, you could plug in 4 days, and at 4 days, it would tell us how the price is going to change and how the units are going to change. So it could say the price is going to go up and the number of units sold are going to go down, that kind of thing. So that's what we're going to be using the implicit differentiation to find, is how is one changing at a certain time, or how is one changing with respect to a different item. That's our related rates. So that's what we'll start on in the next video.